Last week we talked about the third function. And this week we're going to talk about integrable systems. Okay. So first, some physics motivation. So if you have some shallow water wave, so let's say this is your flat ground, and then here's your wave. Shallow means that this length v is significantly longer than the height. Okay. Then this is described by, it's modeled by a KdV equation. And this KdV equation is a PDE. So this is a prototypical example of what is known as integrable PDE. So what this means is that first, we have a large number of explicit solutions. Especially probably the most interesting one are solid tonic solutions. And second, there are infinite numbers of conserved quantity. So these are real physical phenomena, and it turns out that there's a direct connection to this orbit of the vacuum vector under this GL infinity action, which is what we'll be mainly talking about today.
conserved quantity 是什么意思？
就是它，如果你有一个时间维度的话，那它是，比如说你有一个，因为 conserved quantity， 它是不变的。
啊，对。
So we're talking about orbits. So in lecture 4, we had this representation of GL infinity on F0 space, which is the Rn phase. And by the boson-fermion correspondence, we also therefore have the action of these things on the Fock space, on the bosonic Fock space, which is, if you remember, space. And so we use this correspondence to study this orbit. So we have one here, right? One, this is the vacuum vector in B. So it turns out this GL infinity is an infinite dimensional manifold. it turns out we actually know. We know some of these functions. Oh, sorry. So I'll define this to be omega. The orbit is defined to be omega, and we actually know some of these functions in omega. So recall, we talked about the Schur functions previously. This, it turns out, where this lambda is element of partitions, the set of partitions. So lambda here is a partition. They are contained in this orbit. And let us prove it. So by the boson-fermion correspondence, this 1 in V corresponds to this psi naught vacuum vector in F naught space. Now, if you remember, this vacuum vector is defined to be this V0 in F naught is V0, V1, and so on. And the correspondence goes for Schur polynomials. We have some lambda, which is the partition, and we correspond to this psi lambda, which is this Vi on Vi minus 1 dot, where Ik is K for some cutoff for K way smaller. Recall that this means that the Dirac sea, these electrons are all filled, these holes are all filled by electrons. Okay, so we are ready to define an element A of GL infinity. So the action of A is given by exactly what you expect here. So Vk, if it hits Vk, it spits out Vik. This is for k between 0 and k prime minus 1, which is exactly this part, the part they are shifting away from vacuum. Now, and also Vj then is equal to J, it leaves everything untouched for all other J, okay? So then your psi lambda is exactly the representation of this A on psi naught. And because all of the lambda lie in a set of all partitions, and so all of the psi lambdas, therefore, they must be the orbit of GL infinity on the vacuum vector in the F naught space. In the F naught space. And so we have shown that any of the S lambdas, it must lie in omega. Now, because of the boson-fermion correspondence, we can use omega to refer to either the orbit in F naught or B interchangeably. Okay. So in order to relate to ADB equation, we want to show that whenever you have some element of this orbit, this is a solution to an infinite set of PDEs. So this will be the whole point of the first half of today's seminar. So we're going to establish this. Okay. But to understand this, let's first look back at this F0 space. So we want to talk about the defining equations in so we start with a proposition, which is will relate to a defining equation if you have some elements in omega, then this is a solution to some equation which is so this is one of the most important equations today, and I'll keep referring to it as 7.2. This is called 7.2. The defining equation for tau in F0 space. And the proposition also talks about the converse. So it's an if and only if. If you have some tau, you have some non-zero tau, which is in F0 and it satisfies 7.2, then it must be in the orbit. Okay. So we will start by proving the forward direction. If it is in the orbit, then it satisfies this equation. Okay. So first of all, let us look at the vacuum vector. Now, if we have this for j less than or equal to 0, hitting, what this means that is you have this, right? So if j is less than 0, then it must coincide with one of the vj's here. So this is 0. And if you have j star more than or equal to 0, then basically this is a vj more than or equal to 0, which doesn't exist here. Oh, sorry, more than 0. So it doesn't exist in the vacuum vector. So this is also 0. So this shows that the vacuum vector, this satisfies 7.2. Okay. So if I write it out, j vj is equal to 0. So it's a solution. And remember that this in F0 space, this by definition is the form of some element, of the representation of some element of GL infinity acting on psi naught. So this is our GL. Now essentially you can imagine what you want. You have this satisfies, you want this satisfies. So you imagine something like you want to multiply this R0A on the whole 7.2, right? This is what you want to do. Now, if you try to hit this, then you should have something like AVJ. Okay, let's say I add on this part first. Okay, you want something like AVJ. AV naught, AV minus 1, and so on. Okay. So you realize that what's going on here is that essentially you have this hitting your sine naught. Okay. But this thing is clearly not just, it's not this, right? Because this thing hits everything else as well. Or you want just this term, addition of this term. So you want to find out the action of this on this, of this A on Vj. So the answer is that you have R naught A Vj and R naught A inverse. This, because of linearity, this is also R A. And this is because your sine naught, this is V naught, V minus 1, and so on. Now, if you hit it with this first, then all of them get a minus 1, A minus 1. Now, if you hit it with V, then this gives you Vj, right? And finally, you hit it with R naught A. This gives you A here, but everywhere else you have A inverse, and it cancels. So it gives you exactly A Vj with whatever you put in initially. Okay, so that's why we have this term here. So on a very similar note, the dual will have A inverse transpose of This is what you want. Sorry. This is what you want. This is what you want. Okay. And the reason the transpose is here is because you want to have something like this. You want something like this to hold. So the way this transforms, this is R naught A star R naught. Yeah, good morning. What page are we on?
66.
Okay. Yeah. So we're talking about transformation of VJs. So we want to express this A in the basis. So in the basis of VJs, we have this is Aij, the matrix elements. And for A inverse, I think there's a transpose here as well. This is I. There's no transpose. So A inverse is this. Okay. So what this means is that you have A hitting Vj. This gives you Aij, Jivi, sum over I, and then when you have A inverse transpose hitting V star J, then this gives you a Kj Vk star, a bar Kj. And of course, given that we have the relation here, then the sum of A bar Kj Aki sum over j is exactly delta Ki. Okay, and we will sub this relationship into the whole equation. Okay. So from the relationship we had before, now all of this reduced by exactly what we had just now. So we have a sum over ij and k. And this is Abi V I P and B star B star K. Equals to 0. Then using this Aki, Akj thing, the sum over j, this is delta Ki. So we sub this in, and what we have is then your V which is exactly what we wanted. So now this is the forward direction proved. Okay. So there's a remark which is very useful later. So what we have here is that any tau satisfies this very important equation 7.2, which is basically having the V eat the tau. This is equals to 0 in 7.2. Now, in particular, any semi-infinite monomial satisfies 7.2. And the reason why this is important is because for this backward direction, essentially what we're trying to prove is that any tau that satisfies 7.2 must be a semi-infinite monomial. Okay. So now let's move on with the proof in this direction. So first, of course, we assume that one such tau exists, and we want to show that it is a semi-infinite monomial. But a priori, we do not know whether it is semi-infinite monomial. All we know that it must be a linear combination. Tau must be a linear combination of semi-infinite monomials that satisfies 7.2. Each of them satisfies 7.2. And so this T must be some CKTK. Each of these is a semi-infinite monomial. And with T naught having the greatest principal degree, and we assume C naught is equal to 1. Now we see that if among any of the TKs, okay, sorry, we have one such Ki, which can be written as Eij T naught. Then this term can be killed off by simply replacing T naught with this R naught exponential minus Ci Eij, which again satisfies 7.2. And this procedure will terminate. So this R naught Dij. One application of this is called a factor. So we repeat this over and over again until we do not have any element in this linear combination which is one factor away from T naught. And so by replacing, we define a new object T prime which removes all these one factors. And this is some finite linear combination of things B1, T1 plus B2, T2, and so on, but it terminates. So Bs tau S. Now these are all at least, these are more than equal to two factors away from T naught. So from here on out, we use a trick. The idea is that we are comparing degree. Now this idea is important to keep in mind because what's going to happen is a little bit convoluted. So the first thing we do is we have 7.2, we expand with T prime, right? Satisfying 7.2, we expand it. So remember 7.2 Dj tau prime. Now, if you expand the left hand side, this we rewrite as T naught plus Bi tau I, implicit summation over the i's, and T naught plus Bi tau I. Then you can see that there's going to be T naught terms and there's going to be cross terms. So writing that out explicitly, the left hand side is going to be first term. There's going to be terms with T naught and something else. But because of the symmetry, we can write 2 times Bj Bi. T0 I over I, where this Tij is defined to be exactly this symmetric sum going on. So sum over Vn Ti tau I j plus tau j. So here is going to be the symmetric terms with one copy of T naught, a symmetric terms with 2 copies of T naught, and symmetric terms with no copies of T naught. So here we have this T naught, Bi, Bj, Tij, where J, I and J runs from 1 to S, here as well, runs from 1 to S. Except over here, because of the symmetry, we want to enforce that one side is bigger than the other. So all this convoluted math just means that it gives us some kind of equation which says that since we know that Tii is always 0 because this is exactly 7.2 where they're equivalent. So Ti is always 0 and then all of this math just means just reduce to this equation. So we have Bi T0I plus Bi Bj Tij. which is this thing here. So remember, all of this is just doing a degree comparison. So because T0, as we mentioned previously, T0 has the greatest principal degree, and in particular, it has a greater degree than all your TIs, the rest of the TIs. So both terms, they sum independently to 0. Furthermore, this T0, T0I, they are linearly independent, and so each of them must be equal to 0. This is for all I, all the way to S. And so let's look at the first sum. Look at this sum here. This T01 thing going on. So what we have is that sum n T0 plus the symmetric term. I'm going to call this A, this term. Now this is a subtle argument. So if A does not vanish, for some n equals to P, it doesn't vanish. Then there must be some compensating term here. Okay. For some other n. And this is possible only if we have this kind of relationship. For P, some P, Pi is equals to plus or minus the same term Q for T0. Okay. This is only possible if this happens. However, previously we have removed all one factor terms, and note that this is exactly the fact that there is some term here, Ti, which is one factor away from T0. So it's not possible. So it's not possible. And so T0, so it's not possible that T0 and Ti differ by only one factor. So all this means is that T prime is exactly equal to T0. And so this, because T prime is an element, therefore the original T is also an element of this. So we have to, well, let's talk about PDEs now. So now we move on to the defining equations. Defining equations for this orbit in space B. So B0. So recall previously we had this isomorphism. This allows us to map this generating function U. And also, I'm switching up the order of my presentation from the book, so don't be alarmed if you think I'm skipping something. But this thing can act on tau, of course. So we have this xu, tau, and here xu again, which is different from what we normally have, on tau. And this can be rewritten as ui minus j, sum over ij, of vi tau tensor v j. So remember what we just had. We had this part. So essentially what we are looking at with the constant term where this u disappears of this x star u object. And recall this proposition we had previously. So we have this ui v minus j thing, and r b and e. This is equals to 1 over 1 minus b over u over v. And to find what dm dij is, essentially we look at the ui v minus j coefficient on the right hand side. Okay, so this setup will be useful for what's going to come next. So based on what we have previously on this, we can extend the isomorphism from f0 to b to f0 tensor f0 to this c with two sets of variables, x prime and x double prime. Okay. And using our previous relation, we have, because remember we are in V0 space, so this goes to gamma u equals to uc exponential sum over j uj xj, xj prime here, and exp minus That's how u transform and x star u transform as star c inverse exponential the negative of this and the positive of this. Okay, so looking back at this object, this transforms to u exp uj xj prime minus xj double prime times exp. Okay. And this thing, this exponential part, we're gonna call this FUU. And I think here there's a typo in the book. So what you really want to do is your 7.2, which is the u0 coefficient of this x tau object. This transforms to your u0 on the right hand side, including this gamma. But here you have a u already. So essentially what you want is find the residual of this gamma object. Because the residual then multiply with this u then gives you u0. Yeah, so I think there's a typo in the book. Right? This wasted a few hours of my life.
Well, it's good to find.
But the book skips too many steps, so you don't know whether they made a mistake or you made a mistake. Okay.
So good for your train.
Okay. So here, I'm not going to introduce the Hirota bilinear equation yet. So here, I want to push on, and I'm going to do a change of variables. So x prime is going to be x minus y, and x double prime is going to be x plus y. And so this means that x prime minus x double prime, this is minus 2y, and del over del x del So here we have a proposition 7. So basically we substitute everything and we arrive at this proposition that for tau not equals to 0 element of omega, this is true only if the coefficient of u naught vanish in basically this equation with the substitution. So you have u, and then your exp explicitly will be in terms of y. So 2u j y j, and j more equals to 1 exp j more equals to 1 u minus j over j del over del yj times x minus y. So you notice what's going on. Essentially, we have simplified the exponential part by this change of variables, but we have complicated this. And so what we want to do in the next part is that we want to deal with this part. It's too ugly. So that's the entirety of the next section we'll be doing this. Now, first we look at this. This should look familiar from last week. This is the generating functional for our Sure polynomials. And similarly, this is also the same. And so we'll rewrite this in terms of the Sure polynomials. So what is this del y object? Well, del y essentially means you have this del over del y1, del 1 over half del y2, 1/3 del y3, and so on. Which this notation I'll denote as a tuple with so it's 1 over j del over del y. So this notation will refer to this in the future. So now let us look at the u naught coefficient. If you collect these things, then you notice that because there is extra u here, this thing must raise minus j minus 1. So then what's going on is that the u naught coefficient you have sj minus 2y and sj plus 1 of this del y multiplied by tau x minus y tau x plus 1 0. Okay. And if we just look at this part first, so there's going to be a standard trick in this in Hirota bilinear equation, which I haven't introduced yet. I'll introduce shortly. Standard trick is as follows. So first we think about x. We think about this object. And this is f prime x minus y, because there's only one copy of y, so this is what happens. And this is the equivalent to del u f x minus y minus u at u equals to 0. And this is because if you do this, then we get f prime x plus y, x minus y minus u, and u equals to 0.
Is there a manual sign for partial line?
There's a what?
Manual.
Oh, I see. Yeah, there is. There's a sign here. Yeah. So this is this, and thank you. And this gives you. So you can see that it's the same, and this trick will be used very often later. So over here, using this exact trick, then we are gonna have this. So I'm just now considering this part only. This gives you sj plus 1 del y del u. Okay, it's del u, and gx minus y minus u, gx plus y plus u, and u equals to 0. And well, if you look at this object, there's another trick we introduced last week, which this can be rewritten as exp sum of ys del over del us. And this counter. Now this is the shifting operator trick, shifting trick we've seen before. So exp, remember from last week, if you have some exponential yi del over del xi on px, this is equal to py, and you evaluate this at x equals to 0. So we'll be using this trick from last week. Now I'm going to introduce the Hirota bilinear equation. So for me, this is just it's a change in notation essentially. So here comes the definition. So if you have some polynomial x1, depending on some finite number of xn's, then you have some other functions f and g, functions. Then in the Hirota bilinear equation notation, then p acting on f and g is defined to be p del over del u, u1 del over del u2 on f x1 minus u1, x2 minus u2, and so on, multiplied by g x1 plus u1 x2 plus u2 at u equals to 0, where this u of course is the whole set of ui's. So this Pf dot g is equal to 0. This is known as the Hirota bilinear equation. Now for some examples. So first, if you have p equals to x, then what do you have? Pf dot g is del over del u1. Del over del u. So it's f x minus u g x plus u. And the whole thing is evaluated at 0, and this gives you minus g del xf plus f del x. Now if you have t equals to xn, then there's a series expansion you can do, and essentially, eventually you get n equals to 0, k minus 1, k n equals k del k f del u k. Oh, this is sorry. Del x k. So we'll be using this now, and before that one, a remark is that pf dot f is equal to 0 if and only if px equals to minus p minus x.
Why?
Oh, I didn't work this out. I didn't work this out. I just it's stupid to be true. I think it's just a odd and even thing for this part.
Can you see from this?
So I think this, if you have an f here, right?
Yeah.
Then you have this. This is symmetric in k. So this part is the one that is not. And then so if you have one of this, you are replacing this minus x. And I think that gives you the cancellation.
Do you understand?
I think so. I think that's what's going on. Okay, so if you have P, F, F, let's say you just look at this extent, right? Then you will have this sum minus 1 k n k. But if you're del k f del x k del n minus k f del x n minus k. Then you sum.
What's x k means x.
Then I think you have this p minus x thing going on. Then you will have this and this. Yeah, but I think those things will cancel. And then I think there must be some symmetry argument going on here.
If p equal x, it's 0. Why is it?
If
The simplest case. P
oh,
equal
here. Yeah, this is f. This will be 0. Yeah.
And
If you have 1 minus x, then you minus. It's the same thing.
so if part is probably okay, but only if part is 1.
It's only when it's odd that you will cancel.
Do you stay like this one?
So, binomial series is what's it called? Leibniz formula.
Because it's your homework to explain.
Okay. Okay. Okay, so using this new notation we have, let's rewrite what we had previously. So we have this sj plus 1. Remember we previously had u, now we will write as x tilde and exponential of ys xs. s equals to 1 of Tx. So because of this Hirota bilinear equation thing, this thing essentially acts as the del over del u thing we have. And so this x tilde is going to be defined as this 1 over jxj. So then basically this is the equation that we want, because we have fixed the problem of this x plus y, x minus y thing. We have now this tau x. So we'll write the result as a theorem. So theorem. Now this tau is element of this if is a solution. Okay, so and this HB is written as explicitly as -2y, so j equals to 0 of sj plus 1 delta dx. This y1, y2, these are free parameters. And this equation is 7.15. And so given this master equation, we can start talking about the relation to this KdV via what is known as a Kp hierarchy. First of all, we expand. If we expand it in some multivariate Taylor series in these three parameters y1, y2, and so on, then each of these coefficients must vanish. Now this will give us non-linear PDEs. So, well, if we consider a particular y, so yr, then yr in the exponential, it only appears once, which is as yr xr. It appears only once with xr, and then in the sj minus 2y, it only appears in sr minus 2y with coefficient minus 2. Coefficient minus 2. Now then, if we start collecting coefficients, then we have xr, x1 minus 2, sr plus 1. And let's examine a few cases of R. We'll be using this S lambda X definition we've given last week. So this XR X1 minus S 2S R plus 1 this part equals to, if r is equals to 1, 2, and 3. When r is equals to 1, we have minus x2. And when it's 2, it's minus x1 cubed over 3 minus 2x cubed over 3. Oh, sorry, x3 over 3. And for 3, it is, when I start becoming monstrous. So x1, x3 over 3. So using the homework result, it turns out that only the odd terms are all cubed. So in particular, there's 3 things here, so it's cubed. And this one is cubed as well. So these 3 terms survive. So once we drop all the odd monomials, this over here you can see this is trivial. These are all odd terms. So 1 and 2 is trivial. And for the third one, we have this Hirota equation. This P tau tau equals to 0 and P is equals to x1 4 plus 3x2 squared minus 4x1 x3, where we have scaled by a constant. And remember, this thing actually hits, this P hits as del over del something, right? So writing it explicitly in terms of these differential operators, we will have del u 1 4 plus 3 del squared over del u 2 squared minus 4 squared over del u 1 del 2. And remember, we have this tau x plus u tau x minus u thing going on here, and evaluate at u equals to 0. So we're going to write it in a particular way to make connection with the KdV equation. So x1, we're going to write it as x. x2, we're going to write it as y. And x3, we're going to write it as t. And there's a trick involved which introduces a new function. So whatever we have here, tau, is going to be packaged up in this new function to make it look like the KdV equation. So this will be 2 del squared del x squared, where x is now this previous x1 thing. This will be the log of tau. And after you calculate, this gives you the Kp equation. So this is 3 over 4 Okay. So this is exactly the KdV equation, except that I think there's some constant that is different. But anyway, so essentially, if y is independent of u is independent of y, this side goes to 0, then we have exactly the KdV equation. Now up to some constant. So here, remember that we're thinking what are the solutions, right? And at the start of today's seminar, we have shown that these S lambdas, they satisfy the where is in the orbit. And so one particular solution would then be 2L squared over del x squared log of S lambda y t C4, C5, and so on, where these things, they are arbitrary constants. So this is a solution, and this is known as this corollary 7.1. So the remark is that this family of previously we had a family, we had this Sj plus 1 tau tau thing. This family of non-linear equations, this is called the KP hierarchy. And the solutions of this KP hierarchy are parameterized by infinite dimensional homogeneous space. And the rest of the remark I'm going to skip, as well as the next remark about the universal Grassmann manifold, because I have no idea what it's talking about. And we'll skip right to the end.
So this fermion appear as inf-dim Grassmann. You can consider it as a section.
Oh, okay, thank you. Yeah, I've heard of this thing before, but I never studied. Okay, so let's move on to the end solidity solutions. So it turns out there's another class of solutions, and we have, these are known as n-soliton solutions. So recall that previously we had this GL infinity representation in this C, and this is defined by this vertex operator. And the definition is this. So if you have some element A in GL infinity, then exponentiating it, this gives you an element in the linear, general linear group GL infinity. And so we're considering something like exp of A, where now A is some constant of some element here. So as part of the solution, it turns out that this exp A gamma can be thought of as as 1 plus A. And now we'll show why. So this is a proposition. Well, this gamma uv squared. Squared is here. Tau is equal to 0 for good formal power series.
group.
Yeah, so we'll come to that. We'll come to that. In the proof, we'll talk about what it means by group. Okay, so here goes the proof. So by Taylor's formula, remember we just remind ourselves of these lambda things. This shifting things. So this gives tau x1, x2. This gives you tau x1 plus lambda 1, x2 plus lambda 2, and so on. And so if you have something like gamma uv hitting this tau, if you focus on one of the variables that is dependent on, then this gives you exp uj minus and it replaces the tau by xj to xj minus u minus j minus v minus j over j, and then so on. Okay. So we have to use some commutation relations. This EA EB is equal to EB EA EC, where it's a small c if it is A, B. And there's another relation we have to use, which is not 1 to C, is minus J. And so under the assumption if you have two consecutive actions, u prime v prime on gamma u v on tau xj, then this will be this u prime minus u, v prime minus v on v prime minus u, u prime minus v times this exponential. J minus v prime j times tau xj minus u minus j minus v minus j u prime j minus v prime j. Okay, so this is quite 3.7.22, and this is valid under assumption that this u v is less than it's valid for u not equals to u prime, v not equals to v prime, and then taking the limit of u prime to u, v prime to v, then you get that f u v squared tau equals to 0. So I think what good means is that this whole thing works. Yeah, I'm not sure. The book at least didn't give a proper definition of what it means, but yeah, I don't know. Is there a situation where this wouldn't work? Because I think the assumption here is the analytic continuation thing, and then the limit case. So I think, Yeah, it must be.
No, it's not true that you can do analytic continuation for every proportion.
Oh, okay. Yeah, I guess, I mean, if you have tau is a polynomial, right, then you can always do this, right? Yeah, I think that's what, and that's the assumption of, I mean, what good means. Some you can express as a polynomial, and this might fail.
The condition that is so you can do analytic continuation.
Oh, okay.
So it has to converge in some reason.
Oh, okay. Okay, so there's gonna be a. So this is the result that we'll use. So it's just a identity essentially. And now we're going to come to the class of solutions. So we have this corollary. And this class of solutions is this function tau, which depends on n and also a, u, and v of x. This is 1 plus a1, gamma 1, gamma u1, v1, and 1 plus a2, u2, v2, and so on until it terminates for a finite number of these vectors on 1. This function is a solution of the KP hierarchy. Okay, of course, now we have to show that it is. So the KP hierarchy from this previous equation we had of this Sj plus 1 tau thing. Symbolically, what's going on is that we have some kind of object S, which is we have this Vj, V star j thing acting on this tau. And this operator, it's in F tensor F. Oh, sorry, it acts on F tensor F. And this commutes. The diagonal action of GL.
Is it obvious?
No. I didn't see this yet.
No.
Yeah, I don't actually, I don't understand this part. Because he says the proof of proposition 7.2, but I couldn't see where he uses this thing.
What is proposition?
Yeah, it's page 66. It's something to do with the fact that if you have a vacuum vector, then you have S, this is equal to 0, and then afterwards if you then prove that if you have some action I think it's basically this is what's going on.
Yeah, there's no really. It's not a proof.
Yeah, no. So I think what the book is saying is that this concept is used in the proof, and so and so it commutes. Yeah, but I don't know why it's just a diagonal action. I think because Okay. Yeah.
Okay. But in the proof of 7.2, he uses the action of group.
Yeah, because I think you have some R not A, the A is part of the GL infinity, and therefore you use the GL infinity action. Yeah, because the tau, right, is gonna be some R not A. This.
So the equation just after 7.6.
Yeah.
So this seems to be saying that commutes with what is S.
Yeah. S is this VV, V cap.
So this equation seems to be the no.
Mm.
I don't really understand this. Yeah. Yeah, this seems to be.
But where's the diagonal part?
Hmm?
What makes it diagonal?
So this is diagonal action. So a joint action of G remain on S is 0. That's what it says.
Sorry, which part?
So this equation,
This is diagonal.
yeah.
But this, I thought this A can be general, right? This R naught A can be general.
What do you mean general?
So it could be any element in GL infinity. Why does it have to be a diagonal action of GL infinity?
So this is diagonal action. So that's good.
This is that function.
Diagonal action means it act as tensor.
Oh, okay. I didn't know that. Oh, I see. Okay. Oh, okay. I get it now. And well, all of the examples we've seen, they are diagonal then. Because whenever you have some A acting on some V, then this becomes A, V.
Yeah. So of course, yeah. So probably only way you can define.
Okay. Okay, so we know that it commutes. And so there's the argument is that this F, this gamma UV, this gamma UV lies in the completion. That's the completion of GL infinity. And we then have this commuting thing.
It's okay with you?
Yeah. Because this is part, this X on the GL thing.
So because it's a Lie algebra, it's not.
Yeah. Okay, and we want to show that is this 1 plus A of this is in the Lie group. So, but we have another identity here is gamma tau is F squared tau x, but the tau tensor tau minus gamma squared tau tensor tau and gamma squared tau tensor tau minus tau tensor gamma tau equals to 0.
Square.
Oh, yeah, squared. Thanks. So we deduce from this equation we have here from the top that yes. So basically it shows that if you have tau is a solution of this KP hierarchy, then this 1 plus A gamma, using what we just showed previously of this this gamma square is 0. So 1 plus A gamma is also a solution. Acting on tau is also a solution. And so because tau equals to 1 is a solution, then this whole thing, this is a solution. So the corollary is proven. And now let's examine one of the solutions. So first, remember we have this tau, it depends on n, a, u, v. Now this n dictates essentially how many 1 plus a gamma factors you are tacking on to 1, and then this a controls this constant. Okay, so we look at one soliton solution. Each of these factors is then known as a soliton. One soliton solution for a equals to 1, we have this u x y e is equals to 2 del squared log tau 1 u v x. So let's define this thing. Here it's tau 1 u v defined to be is equals to 1 plus gamma, where a equals to 1, times 1. So this is going to be 1 plus exponential of u minus v x plus u squared minus u squared minus v squared. This c is a constant. Okay, and so remember u is hitting this entire thing with this long and then del square. So once we expand, then what we're gonna get is u x y this is equals to u minus v squared over 2 times 1 over whole thing cosh. So this is the one soliton solution. One soliton solution of the KP equation. So recall that we had this u, v, gamma, u, v thing previously, and we can extend this to un. So this allows us to write down an explicit formula for the n soliton solutions. So n soliton solutions. So this involves hitting this gamma u1 v1 all the way to gamma un vn dot 1 is equals to the product of 1 I j strictly larger than I and all the way to n is uj minus ui vj minus And finally, so using this, we will have our explicit expression for tau n a u and v. So this is equals to and so the Kp gradient solution will then be the 2 del del x squared of the log of this thing. So that's the end of lecture 7.